Okay, hello everyone. My name is Matthias, and I'm going to talk about a relatively new feature that was added to MLIR a while ago, which allows you to basically build undefined behavior sanitizers in MLIR. So just a brief overview of what I'm going to talk about. I'm going to briefly mention compile time operation verification, which you're probably familiar with. Then talk about how that's different from runtime operation verification, which is the new feature that I want to talk about. It's based on an op interface, the runtime verifiable op interface. Then a kind of useful tool that I built on top of it, a memory leak sanitizer. And finally, some limitations and future work. So operation verification, you're probably familiar with this, is one of the most fundamental features of MLIR. So the operation verifier runs between passes, or you can also run it manually if you want, and it checks for certain invariants of operations. And some of these invariants that are being checked are auto-generated. For example, if you have your table gen and you put an all types match on the operands, then the verifier will automatically check that these are the same when it passes, when it checks the IR. And some of this can also be handwritten. So basically, you can implement this verify function for your operation, and you can check additional invariants there. So maybe, for example, for a matmul, you want to check that the rank is always a rank 2, or if it's a batch matmul, that it's a rank 3, stuff like that. So one important rule here, this is taken from the MLIR website. There are certain things that you can check in a verifier and certain things that you're not supposed to check. So basically, the guideline is you only want to check things that are local to an operation, only things that you can verify by looking at the operation itself. So what that means is, for example, you're not supposed to take a look at an operand and then go to its defining operation and then check some invariants based on that operation. Everything should be local. The overall purpose of the operation verifier is to build a robust compiler. So basically, if there's something wrong with the operation, you will get an error when you parse the MLIR file, or when parse generates invalid IR, you get an immediate error. And that is also particularly useful for MLIR beginners, because it may tell you that something is wrong with your IR. Maybe you understood the operation incorrectly, and this will give you some hint what's going on. So here's an example. Tensor.extract slice, you're probably familiar with this operation. So this takes a source tensor and it extracts a slice from it, in this case a slice of size 5 at offset 2. And the last number here is a stride, but we don't have to worry about this for this presentation. So this is a valid operation, everything is fine here. So here's an invalid operation. So here we extract, again, a slice of size 5, but we extract it at an offset of 8. And this is incorrect because the slice runs out of bounds. And you get this error message here. So now, what about this operation? Here we have a dynamic offset. So here we extract, again, a slice of size 5, but we don't really know where the slice starts. It starts at % offset. And in the absence of any more information, well, basically we say this operation is valid. We don't really know at compile time whether this extraction will run out of bounds or not, so we allow it. So this is a valid operation. Now, what about this here? So now we have some more information. So the offset is actually a constant, and constant of 8. So at runtime, this thing will run out of bounds. But again, because of the rule that I mentioned earlier, you're only supposed to verify things that are local to an operation. We're not supposed to take a look at the defining op of this % offset, which will tell us that this will run out of bounds. So for that reason, this operation is also valid. So the op verifier will let this through. And more generally speaking, in most cases, we don't actually know what the offset is. If we have a dynamic SSA value here, maybe this is coming in from a function, so you have really no idea what the offset is at runtime. So this is where runtime operation verification comes in. So this is basically a mechanism to generate additional runtime checks similar to C or C++ assertions that will, in this case, generates additional IR, so we check whether at runtime the slice runs out of bounds or not. And the error message that you see here, it's actually quite similar to the error message that would be produced by the static op verifier. So that's what I'm going to talk about in this talk. So runtime operation verification. So there are two things that you need for this if you want to use runtime verification. There's an op interface, the runtime verifiable op interface. It's a very simple op interface. It only has one interface method. And that interface method, the only thing it does is inserts additional IR that checks the invariants that you're interested in. Typically, at the end, it inserts a cf.assert operation, which is somewhat similar to an assertion in C or C++. And also there's the generate runtime verification pass. That's a pass in MLIR that will basically just go over all operations in your module, check if the operation implements this interface, and if so, it will call the interface method to generate the runtime verification code. So here's an example how that could be implemented for the tensor.dim operation. So what you have to know about tensor.dim is it gives you the size of a dimension, in this case %dim. And tensor.dim works for ranked memrefs and for unranked memrefs. So that's the current design in the tensor dialect. Meaning at runtime, maybe this %t, so this is a unranked tensor here, we don't know what the number of dimensions are here. So maybe you're trying to query the size of the second dimension, but this thing is only 1D. So this is something that that is obviously incorrect. You cannot query that dimension if it doesn't exist. So that's something you can check with runtime op verification. So this is how you would implement, or this is actually how it is implemented today. All of this is an external model. So that's just an implementation detail, but that's one way in MLIR to implement op interfaces. And then the implementation is quite simple. So basically we query the rank of the %t, that's the rank here. And then we need two checks. We have to make sure that the dimension that we're querying is greater or equal than 0, and it is smaller than the rank. So if both of those are the case, everything is fine. Otherwise, we should generate an error message. And for that, we create this control flow.assert operation, kind of like a C assertion. And we have this helper function here, which generates a nice error message for us. So it will basically print index is out of bounds. And in addition to that, it will also print the operation as a string. And it will also give you some line information so you can trace it back. OK, this is the operation that fails to verify at runtime. So what we end up now with is a cf.assert operation. And there are two ways to lower that operation. The default way is to use the convert control flow to LLVM pass, or the convert to LLVM pass, which is kind of a catch-all pass that lowers all operations to LLVM if possible. And that will just basically check the assertion, and if it fails, it prints an error message, and then it aborts the program. So if you write an integration test, or if you want to test the runtime verification itself, there's a different way to lower it. There's also this test cf assert pass, which will basically just check the condition and then print the error if the condition is not satisfied, but then the program keeps running. So this is useful to write integration tests for the runtime verification itself, because sometimes you want to use the same test setup and then check like that multiple error messages are being emitted. So this is for integration tests. So now one important question: what should you verify as part of runtime op verification? So basically, what you want to verify are conditions that are classified as undefined behavior in MLIR. And to do that, basically take a look at the op documentation in the table gen and look for the conditions that are mentioned as, okay, if you do this, it's undefined behavior. In practice, the documentation is unfortunately often incomplete. So what you can do is you can take a look at the static op verifier, look for certain conditions that the static op verifier is checking, and then translate that to a dynamic setting. So that's what we had earlier with the extract slice, right? The static op verifier checks that the slice is in bounds when all the compile time information is there, when all the offset sizes and so on are static. And now translate that to the dynamic setting, just check the same thing based on actual SSA values. So now there are also some things that you should not verify. And these are basically, first category is conditions that lead to poison semantics. And an example for that is arith.addI. So poison is basically undefined behavior, but it's deferred. So the operation does not produce immediate undefined behavior, but only if you use the poison value in a certain way, at that point the behavior may be undefined. So for example, for the arith.addI, we have these no signed wrap and no unsigned wrap bits, which will basically tell the compiler, well, this addition is guaranteed to never overflow, but if it overflows anyway, it is not undefined behavior immediately, but only if you use that poison value later in a certain way. For example, you do a control flow branch based on that value, at that point, that will cause undefined behavior. So that's not something you can check with runtime op verification, because at the point of time where this thing here fails, where this assumption here fails, there's no undefined behavior yet. It only materializes later. So that's one category. The second category is, for efficiency reasons, you should also only check invariants that you don't already check as part of the static op verifier. And that's just because we don't want to emit redundant codes. We don't want to emit IR that doesn't do anything. So here's a brief overview of the operations that are supported in MLIR today that support runtime op verification. And the list is still quite short because, well, this is a pretty new feature. But we have good coverage of the memref dialect. And basically, this falls into kind of two categories. Out-of-bound access is something that we typically verify. But another one that's, I think, really useful is memref.cast. And that operation will basically allow you to convert an unranked memref into a ranked memref. That's one of the conversions that you can do. And I think this is a source of, this is an operation, if it goes wrong, it can introduce horrible bugs that fail later and give you weird crashes. So I think this is a particularly useful thing to verify. So the same thing we also support on the tensor dialect, by the way. The list of operation here is still quite short because I didn't get around to implement the interface for more operations. An interesting one that was contributed by somebody, I don't actually know from which company, but we have verification for linalg structured ops. And what you have to know for linalg structured ops is that, well, we have, for example, for linalg generic, we have ins and outs. And depending on the iterator types and the indexing maps, there are certain requirements for the sizes of the dimensions. So for example, here, the requirement is that the dynamic size of this question mark here in %A and %B must be the same at runtime. So that's something that the runtime verifiable op interface implementation verifies. So this could be also quite useful. So let me briefly talk about how to add verification for your own dialect or even to a dialect in MLIR. So typically, the runtime verifiable op interface is implemented as an external model. At least that's how we do it in MLIR. You can also implement it on the operation itself. If it is implemented as an external model, you have to make sure to load the external model. In MLIR, there's this file init_all_dialects.h where we do that. In your own compiler, you probably have some similar file which loads all the dialects and extensions. Also declare the runtime verifiable op interface as promised if you go with the external model approach. And as a kind of best practice, we usually add one test file per operation. For example, we have one test file for memref.cast. And then in there, we have a bunch of tests, and these fall into two categories. So we have positive and negative tests. So basically, we want to make sure that we don't trigger an assertion when an operation is valid. That's kind of similar to the round-trip test in MLIR. And also, we have tests that actually produce an error message, and we want to make sure that the right error message is being produced. So that's similar to an invalid test in MLIR. And there's an example here if you're curious how to do that. So the next question is, when should you trigger verification in your compilation pipeline? And I think the general guideline that I would give here is verify early, meaning as early as possible. For example, when you still have a linalg structured op, you may want to verify at that level because you get the program has more semantic information at that point, and you may get better error messages. So verify early. But you can also verify multiple times. You can verify on the linalg level, and then you lower everything to memref. You can verify again. And this may help you to find additional bugs that were introduced by some of your lowering passes. And finally, only verify in debug builds. The reason for that is that runtime verification can have a quite significant runtime overhead because we insert extra code for every tensor operation, for example. So here's a kind of toy project that I started, that I built on top of runtime op verification. So I used this to build a memory leak sanitizer, and I found I used this to fix some memory leaks in MLIR integration tests. So if you're interested in that, there's a prototype on GitHub. If you find this useful, let me know. I can clean it up, and maybe we can put this land this in MLIR itself. So basically what this detects is it detects memory leaks. That means a memref alloc, but without a matching memref alloc. And it also detects double freeze. So for example, a memref alloc that happens twice for the same memref.alloc. So the basic idea here is that we generate we have a runtime verification implementation for both memrefs and memrefs. And as part of the memrefs verification, we have a call, we insert a call to this runner utils.cpp, which is the MLIR runtime, kind of MLIR runtime library for integration tests. And that thing maintains a kind of hash map for pointers or buffers that were allocated. So whenever we see a memrefs, we put, and we run it at runtime, we put an item into this list, into this map of things that were allocated. And we have a memrefs, we look through that list and we remove it again. And then at the very end, when the program is done executing, we check, is there anything left in this map? And if so, we found a memory leak. So that's the basic idea here. So this is kind of, there's a simple test case here, memrefs without a dalloc, and this is how we would run the test case. There's also the standard LLVM sanitizer. So if you build LLVM with this LLVM use sanitizer equals address, memory leaks are also detected, but you get this kind of, well, not that useful error message. Basically, it tells you you have a malloc here, but no free, but you don't really know where did that happen. There's no information here. So with the runtime verification implementation, the error message looks as follows. So you see again the memrefs, that is the one that was allocated but not deallocated, and it will give you a line number. So you will see, okay, in line 13, that's where the alloc was that leaked. So this is a bit more useful than this cryptic error message here. The reason why I didn't submit this as a pull request yet, by the way, is because I'm not sure if maybe this sanitizer here, the LLVM sanitizer, I'm not super familiar with it, but maybe it could be improved to have line numbers into an MLIR program. So I'm actually not sure if the runtime verification, this memory leak sanitizer approach is the right way to do it. It's just one way to do it, and it was kind of a fun project, and it helped me find some memory leaks. So if you find it useful, let me know. If you know a better way to do it, also let me know. Okay, some limitations and future work. So first of all, I think we need some more customization options. The generate runtime verification path is quite simple. It doesn't have any customization options at the moment. I think we will have to classify the kind of things that we want to verify into different categories, kind of like the undefined behavior sanitizer in LLVM, which has a lot of flags and a lot of different things that you want to look for. And you can selectively enable checks only for, I don't know, for pointer checking or stuff like that. Also, we probably need a way to trigger verification only for specific operations or dialects. Then one kind of open question is, what kind of IR are you allowed to generate as part of the runtime verifiable op interface? So because every operation that you generate as part of the interface implementation has to be lowered further. So for example, if you insert a loop there, an SCF for loop, you have to make sure to run the SCF to control flow lowering pass. So because your interface emits certain operations, you may have to add additional passes to your compilation pipeline, which is that you could have that is kind of not a nice thing about this design here. So this is something we have to think about. Poison semantics, I already mentioned it earlier. Poison semantics means deferred undefined behavior. And it looks like MLIR is, that's at least my impression, MLIR is moving more and more towards poison semantics. And poison semantics is not something that we can check with runtime op verification. So you can build a verifier for poison semantics, but basically that requires you to lower values in a different way. Basically, you have to lower things to, the original lowering type plus an I1 value, which will tell you if it's poisoned or not. So the current approach that I presented here does not work for poison semantics. And MLIR is moving more towards poison semantics, which raises the question, how useful is this feature actually? Maybe if eventually all kind of undefined behavior that we have in MLIR is poison semantics, then there's nothing to verify. So kind of an open question here. And finally, I think we should start investing also in better error messages. So this is the error message for the current error message for the extract slice that runs out of bounds. And if you compare that with the static op verifier, it doesn't give you as much information because it doesn't print why the dimension ran out of bounds. So I think we could improve this by adding a format string to cf.assert plus SSA values that should be printed, or maybe even add a new operation at all for runtime verification in particular. All right, that brings me to the end of my talk, and I'm happy to answer any questions.
Any questions?
Thank you. MLIR has have higher level dialect and lower level dialect. So, and it can mixed in one IR. So, and when lowering, unchanged OP can be exist. So, I want and the runtime assertions can be inserted multiple times. But so I'm wondering that um, it is it intended to insert multiple assertions to the unchanged OP? So it is so when assertion it is um, multiple same errors emitted.
That's a good point. So I think in practice, when you run the program, it's not that big of a issue because the moment you hit the first assertion, the program crashes. So from if you think about how many checks do we, well, no, even if you run, the assertion may pass. So if the assertion passes and then you generate, yeah, you have the same operation that you verified multiple times, you do redundant checks. Yeah, that is a problem. Good point. There's no easy way to fix it because so the way you generate runtime verification is you run the generate runtime verification pass. So if you have, in your scenario, you would run this pass multiple times. You run it like early in the compilation pipeline and then again later, you verify the same operation again. So you would have to share some information between these two runs of the pass. And MLIR right now does not have a good way to pass information between pass boundaries. So that is a problem. I think in practice, it is less of a problem because at least in the compilation pipelines that I've seen, there's a kind of clear boundary. So it doesn't, at least in my experience, it doesn't happen that much that the exact same operations. So usually there's like a clear lowering pipeline. Okay, you have like high-level operations, and then I run some pass, and all the high-level operations are gone, and now I'm linalg level, and then I'm on the memref level. So in practice, I didn't run into this issue that often, where the same operation persists through many. Well, it may persist through many passes, but then you can still play with a point where you want to insert the runtime verification pass. So I think in practice, you just have to find good places where to insert your runtime verification pass, and I think if you play with that, you can probably avoid generating redundant verification code.
Hi, thank you for the talk. Has there been significant use cases recently for this runtime op verification interface?
So it's a pretty new feature. I think it's not used a lot, but the linalg verification was implemented by, I forgot from which company, but somebody found this feature. I did not really advertise it. There was an RFC a long time ago, 2 years ago, and implemented the runtime verification. And then a year later, somebody implemented the verification for linalg generic. And I think what happened there is that the operation, if you look at it at first, it's quite complex. And I remember when I learned about it for the first time, I was confused for a long time. And what always helped me is looking at the error message when the static op verifier failed. And I think that person ran into the same issue, but didn't get an error message because all the dimensions were question marks. So I think the main use cases that exist today is just probably for beginners of MLIR who want to understand, is my program does not work as intended? Am I using it incorrectly? I think that's the main use case.
Thank you.
Hi, thanks for the talk. Have you measured if there's a compile time or runtime overhead associated with this?
I have not measured it, but I expect the overhead to be quite large. Because for every, if you're on a memref level, for every single operation you insert additional checks, so the IR already doubles. Actually, it more than doubles, because you need the cf.assert, and you need something that generates the condition value. And then for some operations, like memref.subview, there are many things to check. So basically, for every dimension, you have to check that, okay, it's greater, that it doesn't run out of bounds. So the IR kind of explodes by doing that. That's why I mentioned this is only something to do. This is only something you should do when you run in a debug mode. I expect this to be at least like 2x slower than without runtime verification.
All right, thank you so much, Matthias. Let's give Matthias a hand.